All right, so this post is going to be about sketching shear and moment diagrams, basically approximating shear and moment diagrams. And the key here, the whole reason we're doing this, is to try to build some intuition. So as you go out and practice structural engineering, you're going to be using a lot of software. And that software is going to be giving you a lot of results, a lot of shear and moment diagrams. And if you don't have any expectation about what the shape, and the relationship between shear and moment diagrams should be in those particular cases, then you're going to actually struggle to, validate those models and, make sure that you can kind of error screen them and, and correct any issues that you have. So this is, actually, I won't say it was a new fundamental because people have thought of this as fundamental for a long time, but it certainly has become more important as people have moved away from hand calculations in current practice and moved more towards, using computational tools. First thing I'm going to do is go through the general process here, and then, which is fairly simple. And then we're going to go through and do a few examples. So one thing to keep in mind as we go through this, and this is something that some students do struggle with, and that is that what we're talking about here is may seem very qualitative and arbitrary to you, as if there are multiple ways that this can be done, right? And I would challenge you, as you go through, these notes and the homeworks that I will post, to see, can you in fact follow all these steps and get, an estimate of a shear and moment diagram that are materially different, right? As you'll see, the scale of them, the value of moment at any particular point, we don't know that simply by doing this in an approximate way. But the general shape, what side's the moment diagram on, and what does it look like, where does roughly it cross zero, and so forth and so on. Those are things that that this method should be able to provide for you, right? So the first step here is to sketch the deflected shape. So one of the reasons why we do this is whether you know it or not, you have some intuition actually about how structures with certain supports and certain applied loads will deform. And so we're going to try to tap into that here. And there's a couple rules here, right? Rule 1 is that you must satisfy boundary conditions and continuity conditions, right? So if two members come together and there's a hinge, well, they have to have the same displacement at that hinge. Doesn't have to be zero, but they can have different rotations, right? So there can sort of be a kink in the deformed shape, right? And then the second one is that we want to minimize curvature reversals. Right? And what we mean by curvature reversals is going from concave up, let's say. Ooh, sorry about that. To concave down. Right? Or vice versa. Right? So if I have a deformed shape that does this, and then I have a deformed, then it continues and it does that, that is one curvature reversal. Right? So basically what we want to do is come up with a deformed shape that satisfies boundary and continuity conditions with the least amount of curvature reversals, right? That's kind of the goal here. So if we do a, just a really simple example, right? And maybe I'll apply a downward force, right? So if I'm going to draw the deformed shape in blue here, it's going to look something like that, right? Now you guys all hopefully know that, right? And we have compression on the top and we have tension on the bottom, and that's going to be really important because the deformed shape shows us which side the moment diagram is going to be plotted on, right? The reason I'm doing this is to show you what would not satisfy the minimum curvature reversals, right? So if I have this same structure, right, and I apply this, I'm writing over on this edge, I end up hitting that button. Right, something like this, right, would not satisfy the minimum curvature reversal, right? You can see it does satisfy the boundary and continuity conditions. The displacement at the pin and the roller are both zero. That's basically the only boundary condition that we have, right? But I have all these curvature reversals in there, and I do not need them, right? I can do this with a single curvature, that is, you know, the entire top of the beam is in compression, the entire bottom of the beam is in tension, right? Where here you see we are flipping compression, right? First it's top of the beam, then bottom, then top, then bottom, etc., etc. That's not needed. Okay, so that's really the only you know, challenging step, because the other ones are basically to follow the rules that we talked about, right? So we're going to draw the moment diagram then, and I always try to draw a moment diagram first. Diagram on the compression side. According to the rules from, and I think I called it the cheat sheet lecture, right? So those sort of provided all of the rules that we needed, right? And then finally we're going to also draw the shear diagram. According to the cheat sheet rules as well. And this guy here, maybe I will try to underline it, right? So on the compression side, that is our local sign convention, right? So this is the local sign convention. So I know we didn't necessarily talk about it like that. We drew our little, you know, squares and we showed the arrows causing compression up. But basically what it means is we plot moment diagrams on the compression side, and that is almost a universal, at least in the US, I should say. That is a very, very widely used convention. I think it's embedded in almost all structural analysis packages, although you can change them. There are settings for that. Okay, so let's do some examples so you can kind of see how this works. So the first example here, I guess I'll do this here. We'll call this example 1. Right. And I'm going to try to go through these somewhat quickly because I think they're fairly straightforward. So let me put a roller here, this guy, and I think we've got a point load, right? So now a couple things you want to notice. First is that I'm not going to give you any numbers, right? I'm not going to dimension anything. And the reason we're not going to do that is because it doesn't matter, right? We're not actually solving for, you know, moment and shear values, right? All we're doing is we're trying to draw the shape of the moment and the shear diagrams, right? So let me just set this up. So this is my shear diagram. And this is my moment diagram in blue. So I am going to draw, I guess I'll do it in well, maybe I'll try to do it in gray here. I'm going to draw the deformed shape, right? So the deformed shape requires that we stay at this pin and we stay at that roller, right? And you can see, since we're pushing this beam down, this guy is going to have to deform downward. I'm going to say it's going to deform there, right? And now what I want to do is sort of connect the dots with the minimum amount of curvature reversals. All right, so let me try that again. It's a little bit hard to do where, there, I think that looks pretty good. Right, so this is my deformed shape in gray, right? One thing that you can see here, hopefully, is that the whole bottom is in compression and the whole top is in tension, right? So if we're going to now draw our moment diagrams based on the rules, right? Well, we have a pin, and there's no pin, there's no moment applied to the pin, so my moment diagram has to be 0 there, right? We also have a free support here, and that free support has no moment applied to it, so my moment has to be 0 there as well, right? And now I have compression on the bottom, so I'm going to highlight, I'm going to highlight the bottom of this beam like this, right? And what I'm saying there is that the entire moment diagram has to be plotted on the bottom, right? Has to be plotted on the bottom of the beam. And because there's no load applied between the pin and the roller, or the roller and the free end, at most the moment diagram has to be linearly varying, right? So this is the only moment diagram that actually satisfies all of those requirements, right? Okay. So we have a change in slope. That's at the roller support, right? Which is basically treated as an applied load, right? An applied point load, right? And then if we look at the shear diagram, right, there's a couple ways to do it. You can follow the rules. I can also look at this moment diagram and say, well, it should be below the axis there, right, because I have a negative slope of my moment diagram. And then it should be above here because I have a positive slope of my moment diagram. And then I'm going to have that jump at the internal support, right, which is equal to the reaction at that roller, right? So from this, you could actually see that the pin here on the left actually has to have a reaction downward. That's what's pushing the shear diagram downward. Then it's constant. Then I have the reaction at the roller that's upwards, right? Then I come over, and then the applied load is downward. Right? So that's the example, right? That's basically what the solution to this looks like. I don't have any numbers. I have no equations, right? Just shapes. Okay, so let's do another example. So this one we will call, of course, example 2. And let me just call it up here. Okay, so this one's a little bit more complicated. We're going to have an internal release. Right, and then we're going to have another support roller here. Then we're going to have a distributed load. All right, and this support here is a fixed support. Right? So let me draw all of these guys down. Ooh, something like that. And let's see, I think we do shear in red. And then we do moment in blue. Okay. So, first thing, as we did in the previous one, is we've got to draw the deformed shape, right? And so this may take a little bit, you know, sort of trial and error here, right? But hopefully what you can see here is this applied load is going to be trying to spin the beam downward like that, right? And that beam is actually resisted by this portion of the beam that's going to move upwards, right? So if that, let me see here. Let me try to erase this guy here. Yeah, like that. So this whole, the right-hand portion is sort of tipping clockwise around the roller, and it's pulling up on the on that left-hand portion of the beam. And so then this guy is going to deform something like this. Right? And if you look, this guy is concave on the top side, so tension on the bottom, and then this whole right-hand member is actually compression on the bottom, tension on the top. Right? That's kind of how it has to deform, right? And if you notice at the moment release at the hinge, they have the same displacement, but they have different rotations, right? Because there's a kink in the hinge, so that's no problem, right? They can actually rotate differently. Right? Okay, so first thing I do is we'll come in here and say, okay, that's concave on the top and concave on the bottom. Right? So that is the direction or the side of the member that I should be plotting my moment diagram on, right? So from the left-hand member here, right, we have no load there. So at most my moment diagram can be linearly varying. And I know that at the hinge, right, at the right-hand side, the moment has to be 0, right? So I know at this point, right, this guy here, my moment has to be 0, right? And I also know that at this point here, all the way over to the free end, that my moment has to be 0, right? And so I know to the left of the hinge, it's got to be plotted on the top, and to the right of the hinge, it's got to be plotted on the bottom. Since there's no load between the fixed support and the roller, at most that can be linearly varying, so it has to look like that. Right? There's no other way it can look. Again, you gotta sort of try it on your own to convince yourself that there's only one solution to these. I know it seems arbitrary, right? And then we're on the bottom, right? So between the roller, or between the hinge, the moment release, and the roller, there's no load. So again, that has to be linearly varying, right? Like that. And then if we look between the roller and the end of the beam, now that is a uniformly distributed load, and so we're going to have a quadratic moment diagram, and that quadratic moment diagram has to be concave in the direction of the load, right? So because the load is pointing downward, the moment diagram is going to be concave downward, like that, right? So that's basically it. Right? That's got to be the moment diagram. You see it's plotted on the compression side based on the deformed shape, and it follows all of the rules that we had put forth before. Right? So now we can do the shear diagram. Right? Shear diagram is a negative slope. Right? Interestingly enough, we also said that a shear diagram is kind of unaffected by a hinge, and you can see here in this case it is, right? That moment diagram actually doesn't change slope there. And then we come to the roller support, right? And we have a jump. And if you look at the slope of the moment diagram, it's positive, meaning going from lower left to upper right, right? And then it goes down to 0. And of course, we know that underneath a distributed load, the shear diagram has to be linearly varying. And so that's that. Again, no numbers. Right? I don't know any of the numbers. I just know that this is what the shape should look like for the for this particular structure. Okay, and that's the shape of the moment and the shear diagram. Okay, last one quickly. I know this video is getting a little long. Okay, so example 3. So I did this one over here. So this guy, we're going to do something like this, and I think I had like that, and I put a point load here, and I put a distributed load on that side. Is that right? Yes, that's right. Okay, so this is actually a statically indeterminate problem, right? We have 4 reactions, we have 3 equations of equilibrium, but I wanted to do this one to show you that the same approximate method has to apply, right? So it still is going to work even though this is a statically indeterminate structure, right? Okay, so then this is my shear diagram, and we'll do our moment diagram here, like that, right? Okay, so this is V, and this is M. Okay, so now we're going to draw our deformed shape, right? And there's a couple sort of variations of the deformed shape, right? But we do know that that point has to be there, this point has to be here, this point has to be here. We know that under this load, this point should move down, right, in general, right? Of course, it depends if the distributed load is really, really big in relation to the point load. This may not always be the case, but for approximate methods, we generally assume the structure moves in the direction of the load, right? And then here, this point moves down as well, right? And so the deformed shape has to look something like this. And if you notice, what I did here is over that center support, right, I cannot have a kink, right? There's no moment release there. So I do need a curvature reversal, right? And so over that support, I have compression on the bottom, tension on the top, and then here is compression, tension, and here is compression, tension, right? So I don't know exactly how long that, that segment is, but there is a segment there where I have compression on the bottom, and then there's a large segment here where I have compression on the top, and there's a big segment here where I have compression on the top. Right? So now if we come to our moment diagram, we know that the moment at the left-hand support has to be 0. We know that the moment at the right-hand support has to be 0, right? Because they're pin and roller supports, there's no applied moment. That center support does not have to have a 0 moment, right? That is an internal support, right? So here, we know the beginning of this, the member on the left, at most can be linearly varying up to the point load. Then we can have a change in slope, and it can be linearly varying again, right? And so the only way for this to work and be plotted on the top side of the member is to do something like this, right? Right. So that is consistent with the point load, right? It's linearly varying, and then it has to cross 0 where we see the deformed shape go to concave down from concave up. Right? And then on the right-hand side, we know that that is a quadratic moment diagram, and we know that it has to cross 0 there, and then it has to come back to 0 here. So just knowing that, we could say, well, it has to be concave down, because that's the only way that could work. But we also know it's concave down because that's the direction that the load is being applied in. Okay. And then if we move to the shear diagram, right? So once I've drawn the moment diagram, shear diagram is pretty easy. This is a positive slope, right? This one is a negative slope, like that. And then this guy here is a positive slope up into a certain point, and then it is a negative slope. And so I'm just going to draw that. And we have a jump where the applied point load is, right? So in general, we would say, okay, well, where that is 0, that's where the moment is maximum. You know, based on this sketch, it's probably a little bit further to the right. But again, we don't have numbers here. I'm not plotting out exactly where it's crossing 0. I'm just looking at the shape, right? So if I run a simulation and it gives me this shear diagram and this moment diagram, then it would have numbers and we would have all these dimensions. I have a gut feel of whether or not that makes sense to me, or maybe I've made a mistake, or maybe I've asked the computer to solve the wrong problem. That's actually pretty common. Okay, so with that, I think we'll end this, and I will answer questions on this on